Welcome back. In this video, we're going to explore a famous and powerful strategy for finding prime numbers, the Sieve of Eratosthenes. This method is old, elegant, and extremely useful for helping students understand what prime numbers really are. We start with a chart of numbers in order. My chart goes from 1 to 100, but this chart can go from 1 to any number. We start by thinking about which numbers are prime. So remember, a prime number has exactly two positive factors, 1 and itself. So let's build this particular sieve. First, we find our first prime number. Remember, 1 is neither, so I'll go ahead and cross it out. 2 is prime, so we circle it. Now, we're going to cross out every multiple of 2 that's greater than 2. So we cross out 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, etc. Why do we cross these out? Because they're divisible by 2, so they are composite. Now we move to the first number that's not crossed out after 2, and that's 3. So we circle 3. Then we cross out every multiple of 3 that's greater than 3. So 6, 9, 12, 15, 18, 21, etc. Some of these, like 6 and 12, may already be crossed out, and that's okay. Now let's continue. Our first number that's not crossed out after 3 is going to be 5. And then we need to cross out all of our multiples of 5. Once again, a lot of these are already crossed out, so it gets easier and easier as we go. Next, we move to 7, and we start crossing out 7's multiples. Continue circling the first number that's not crossed out, and then crossing out its multiples. Next, we have 11. All of its multiples are crossed out. 13, all of its multiples are already done, and we've actually done all of the multiples of every number that's left. So I'll go ahead and circle all of our remaining numbers. And when we're done, we will have circled every prime number. Why? Because every composite number gets crossed out as a multiple of some other smaller number. This activity helps students see that composite numbers are built from smaller factors, while prime numbers remain because they cannot be decomposed that way. Now let's think about how we could use this to find all the prime numbers between 1 and 200. We could create a list or a grid of the numbers from 1 to 200 and then repeat this same process. Circle 2, cross out its multiples. Circle 3, cross out its multiples. Circle 5, cross out its multiples, etc. And an important note, we do not circle 1 because 1 is neither prime nor composite. For a large range, like 1 to 200, this method is systematic and visual. It helps us organize the work rather than guess. And as future teachers, there are several things to notice here. First, this activity reinforces the meaning of multiple and divisible. Second, it gives students repeated experience with skip counting and recognizing structure. Third, it shows that prime numbers are not random. They emerge from a logical process. It can also lead to great classroom conversations. Why do some numbers get crossed out more than once? Why does every composite number eventually get eliminated? Why does 1 not fit into either category? These are the kinds of questions that build real number sense. If this feels like a lot, that is okay. Prime numbers are an idea students revisit many times. What matters is understanding the logic, not rushing through it. In the next video, we'll use factors to break numbers apart with factor trees, and then connect that work to one of the most important ideas in number theory, the fundamental theorem of arithmetic.